Good
So,
evening, everybody, and welcome to tonight's edition of the Triangle Area SQL Server User Group's Advanced DBA meeting. So we have with us, once again, the always outstanding Torsten Strauss, who's going to talk to us today about row and page compression in Azure SQL. So with no further ado, Torsten, please take it away.
yeah, thank you, Kevin. Thanks for the invitation. Thanks for the opportunity to have another talk in your meetup group. And thanks for attending my session. So, as mentioned, the session is about row and page compression in Azure SQL or whatever. So, any kind of flavor of SQL, will support row and page compression. And before I'm going into the deep dive, I just want to introduce myself. So my name is Torsten. I'm located in Germany. I'm a consultant, trainer, and speaker. And maybe the most important one is the email address, which you will find on the screen. So feel free to reach out to me in case of any kind of question with regards to, let's say SQL performance, Azure DevOps, CI/CD, Bicep, and all this kind of stuff. So that's all. And now we will go into the code. It's not a very easy one, to be honest. I mean, it's a deep dive. A deep dive cannot be easy. But I think I have 1 hour time to make you familiar with the idea of row and page compression, how it works. And maybe the first question is you should ask yourself, are you using page or row compression? So if not, I would recommend to consider at least row compression for several reasons. You will see why. Page compression is also something you can use, but this is a little bit more specific. So you really have to understand how it works, the downsides, and also for sure the benefits, and when it makes sense to compress your table by either the row or the page algorithm. Yes, so what I have is just a small database. So I already created the database upfront, called page and row compression. Nothing special about it, just a normal database, no in-memory stuff. So really just a normal traditional database on SQL Server version 2025. Yes, correct. I don't know, it is CTP 1.4, 1.5. I didn't remember anymore. It really doesn't matter because everything I'm going to present is there since 2016. And at least from my understanding, nothing has changed even in SQL Server version 2025. Okay, so let's talk about page and row compression more into detail. First of all, just want to give you a brief understanding about what it is and what kind of benefits you can expect, and maybe also, to pay for the benefits. Nothing is for free. If page and row compression is something you, or the other way around, when you always benefit from row page compression, this would be the default, which is not the case. So therefore, it's up to you to decide when it makes sense and when it doesn't make sense. So, as mentioned, row and page compression was introduced in SQL Server version 2016, so a long time ago, almost 10 years ago. And again, since then, nothing has changed. The feature is, let's say, very reliable. It's a stable feature. I haven't heard anything different to that. So you can use it, but you have to understand the details. So first of all, the idea of having a feature like compression means that I mean, not you, the engine, the storage engine to be precise, has or can, it is not always guaranteed, but it can compress a table by, it seems, two different algorithms, which is either page or row. By the way, we have other kind of compressions as well, which is the column store index, which works differently, but it also has a very high compression. And then we have the archive compression, which is related to column store. This is even an additional and more, let's say, powerful compression with its own disadvantages. So here we are just talking about the traditional rowstore engine, which is a heap, a clustered table, or a non-clustered B tree, so an index. So this is where you can use page and row compression. So first of all, you have to understand when you enable the feature, it has its own overhead. You can imagine when you compress a table, dependent on the number of records you have in your table, and you're going to insert into the table, there's a CPU overhead. I don't want to say it is neglectable. There's definitely a CPU overhead, but I would say in these times where we really have fast CPUs, I would say, again, it is not neglectable, but I would say in most cases, you will not see any kind of performance impact by or page compression. At that time, you apply the algorithm. Because on the other hand, and that is something which is definitely beneficial, is that when you have a compressed version of your table, so the memory impact is definitely reduced, because usually SQL Server uses a so-called fixed variable format, which has its own overhead to save user data in a page. So we will see how to dump a page later on. So page is always 8 kilobyte big. So it has a header of 96 bytes. And then we have a row offset table, which is at least 36 bytes, and it will increase by the number of rows. So now you can imagine we have something in between the header and the row offset table, which is called the payload. So usually you can say you have something about 80-60 bytes, which is the remaining space on the page when you subtract 96 bytes from the header and the row offset table. So and now you can imagine when you have an algorithm which is able to compress the data, and we will talk about compression in detail, you are able, or the storage engine is able to save more information on the same page. So usually your performance will increase or decrease with the number of pages SQL Server has to read. Because when you read a table which isn't in the buffer yet, because the buffer is, I don't know, cold, because you have restarted SQL Server recently, SQL Server has to ask the storage engine to identify the pages on your disk, which is the MDF or NDF file. So, and when the storage engine identify the pages on the disk, it will save all pages in the so-called buffer pool, which is nothing else than all the pages which belongs to the table or the index. So when you now compress data, you can imagine that you need less number of pages in order to save the same amount of information. So, and that is definitely something which is beneficial, especially in a case when you don't write very often into the table. Because you already understand that the algorithm, or the, let's say, when SQL Server have to compress the data, it needs CPU, but once it is compressed, I don't want to say only have, but you have a lot of benefits with regards to the storage allocation in buffer and on disk. So you know that memory is limited. Memory is a limited resource. That means there's only a certain amount of the overall instance memory available. That means there is an indication, a performance counter, which is called PLE, page life expectancy, which will measure the time in average how long a page will stay in memory until the lazy writer process or the checkpoint process will flush a certain amount of pages from the buffer to have remaining space available for a scenario where the storage engine has to read and save additional pages into memory. So, and that is definitely something you want to avoid. So that means when you compress your data, you need less number of pages in memory, which has the positive effect that your PLE is increasing over time. So, and you also have, or it is more likely that SQL Server will find the pages in memory because it is still in memory because of the higher PLE, and it does not have to go to disk in order to have a physical I/O. So that is the idea. Yes. When you have something which is considered to be a so-called singleton lookup, that means you can consider a B tree and you are navigating through the balance tree. So you start at the root level, maybe you go to the first intermediate level, and then you go to the leaf. Compression doesn't make sense because when you just look for a specific record, which is a unique record within your balance tree, in this case, you get one page for the root, one page for the intermediate level, and one page for the leaf. That means when you have a proper index strategy and you don't have forward scan, so let's say range scans, you will not benefit from compression. Of course, you will always read 3 pages, regardless of whether the page is compressed or not. So that means it makes sense to understand your workload and not say in general, you will now apply row or page compression after this session because you now have the feeling it is a good idea. So we will see use cases where it definitely doesn't make sense to implement compression. But this is something you should keep in mind. So when you have a proper index strategy and you're looking for unique value, I don't know, for a specific customer within your customer table, and there's only one, it really doesn't matter as far as you have a B tree, a non-cluster or cluster table, which will give you a navigation through the balance tree to find the record maybe by, I don't know, 2 or 3 page lookups. Okay, again, the good thing about compression is that the compression will remain in memory. So that means we have memory savings as well. So again, memory is limited, therefore that is beneficial. So the problem, I cannot promise to go in or to show every single example. I have a lot of examples here, but I'm pretty sure that I cannot cover this within an hour. But at the very end of my script, you will find an example where we compare a query, I don't know, 1,000 or 1 million records within a table, which isn't compressed, and another scenario where we also save 1 million rows in a compressed table. So when now we ask the query analyzer to figure out or to estimate the so-called subtree cost, the estimated subtree cost. So SQL Server always have to estimate the subtree cost, and the cost is nothing else than I/O, CPU and memory, by the worst scenario. That means the analyzer will always, let's say, will always consider reading all the pages from disk, even though the pages may be already in buffer, which has a complete different impact on your storage engine because you don't need to read the pages. So therefore, the estimated subtree cost is always calculated by the worst scenario, which is also the case when we talk about page or row compression. So the engine doesn't make any difference with regards to the subtree cost, to the cardinality estimation, and therefore to your CPU, memory, and IOs. That means When you run a query on a table which is compressed, and the same query on a table which isn't compressed, the memory grant, the number of IOs which is estimated, will be the same. That means you will not see any cost reduction in your, let's say, in your plan, but for sure you have a much better memory allocation within your buffer, because again, you are able to save more information within the same page. But from a query perspective, so the analyzer, there is no difference. That is something which is very interesting, because you might or you might wonder why your sub-query cost and your memory grant is not going down after you compress your B tree or your heap or whatever. This is because the query estimator is always considering the worst case, which means the table has to be decompressed. Okay, let's go down. So there are some limitations which we will cover later on about partitioning, about non-clustered indexes, which will not inherit the compression property of the table, and so forth. Everything is already proven by examples. Again, I cannot promise to go to every single sample here, but there is definitely something I want to show, because this was also completely new for me. So compressed. Now you are inserting more and more records into the table. Your assumption is, and that was also my assumption, is that the new inserted records will be automatically compressed either by row or page. This is not true, as we will see. It depends whether we have a clustered index, a non-clustered index, or a heap. And the way you are inserting records, when you do it with a tab log, with a BCP or whatever, this is a complete different story. So this is really something which is very interesting when you think about, sometimes you have to load data, I don't know, by some kind of an ETL process or whatever. You want to ingest a lot of data by a bulk insert. You have to understand when SQL Server will apply row page compression and when it will be completely ignored. That means you have the assumption that your page is compressed and you will benefit from all the things which I already mentioned. And finally, you will figure out that the new inserted records are not even compressed because of these, let's say, limitations. So I will go down, because otherwise I cannot share the examples with you. So first of all, what you have to understand is, again, SQL Server always has to consider the worst case. That means SQL Server has to decompress the compressed table. So let's do the following. I will create a table like this. We have an integer. Sorry, we have not an integer. We have two columns. One is a character 8000, and another one which is a character of 53. That means we have two so-called fixed data types. And it doesn't matter whether you save 1 or 8000 bytes in the very first column, you will always allocate 8000 bytes as far as you don't compress the table. So when you now want to compress a table, there is an overhead. So we will see that hopefully we will see later on, that the so-called fixed variable format, which is now used, will be changed due to the compression to a so-called CD, which is the change descriptor format, which has its own overhead per record. So the overhead in our case is 10 bytes. That means when I create a table like this, it works for sure, because the limit is 8060 bytes. So we have 7 bytes overhead for tag A, tag B, and then we have the F size and so forth, which is the null bit. So that means we have 7 bytes overhead for the fixed data type. And when we now want to compress a table, it doesn't work, because SQL Server will already understand I cannot compress a table because I need additional 10 bytes overhead per record. That means sometimes you will figure out that you cannot even compress a table because the length of all the possible bytes, including the new overhead of 10 bytes, which is different to 7 bytes, will not allow you to save or to compress a table. That is a limitation. And I mean, we will understand that this is definitely a limitation, but we cannot change it. So let's go to another example. So let's create a table, another time a heap, or 3 columns this time in integer. Column 1, column 2, all of them are fixed lengths or data types. And we will add a clustered primary key with page compression. So you can see the syntax, alter table, add constraint primary key. So most people are familiar with it. And now we say with data compression is equal to page. Again, we have 2 kind of algorithms. This time it is page. It works because we don't exceed the maximum number of bytes. So we can now go to the we can join several DMVs in order to get the metadata information, and we can see that the heap, sorry, not the heap, the clustered index is page compressed. This is not true because at the point in time we don't even have any kind of record in the table. That means we don't even have any page allocated. That means this is just the description of the clustered index, and within the metadata information of the clustered index, we will see that we applied page compression on the clustered index. But again, we don't even have a page in place yet, and we will see later on that this is something you cannot rely on. So we will see page compression, but we don't have a page compression. We only have a row compression, which is a first level, which is required for page compression. So page compression will happen on top of row compression by a dictionary lookup and all these other fancy stuff. But again, for now, we will keep it. So I think I have it. Now we create a non-clustered B tree, an index, and we don't have any additional compression available. So my understanding so far was, and I'm wrong, that the non-clustered index will automatically inherit the compression type of the underlying table, which is in our case a cluster table. This is not true, which is good because now we can see, first of all, we can prove that we are right. The non-clustered index does not have any kind of compression available. And the good thing about this is when we now we can now rebuild the table as the non-clustered index, which means we are rebuilding the clustered index as well as the non-clustered index. And now we ask another time, nothing changed, which is perfect because now we can decide which kind of compression algorithm we will apply to the non-clustered index. Sometimes, not often, but sometimes it makes sense to have page compression available or maybe row compression available on the clustered table, on the clustered index. And for the non-clustered index, you have a different compression type, which can be page, which can be row, or you decide even not to compress the balance tree. To be honest with you, I don't have any real life example for this scenario, but I have another example where we will cover partitioning, and then it makes sense because we can create indexes on partitions, because for every single partition, or for every single index partition, we will create a complete, separate, and independent B tree. That means when you think about the idea of having partitions, we can have partitions which are already, which will where we save a lot of very old data. So now we can ask ourselves, Does it make sense to have row compression? Does it make sense to have page compression? Or do we even want to go one step further and apply column store compression, or even one step further, which is column store archive compression? So now it's up to us. We can decide which partition, which index should follow which compression type. So yeah, we can now say I have a non-clustered index with a data compression row, which is different to page. And now we can see that we have page and row compression for the B tree as well as for the cluster B tree, which is our cluster table. So interesting, but again, this is not a scenario which you usually have in real projects. So therefore, we will go one step further. And first of all, we should answer the question, which data type will benefit from compression? So we can see that a varchar, a text, and all the other data types, which you can see here, will not benefit from compression because there is no space or no space saving. Let's go. Let's try to understand why. So a varchar is not a fixed data type. Instead, it is a variable length data type. That means when you have a varchar of, I don't know, 8,000 or 4,000 bytes at maximum, and you insert a record into the varchar, let's say 8,000, and you only insert, I don't know, 1,000 bytes, SQL Server internally only saves or requires 1,000 bytes in the payload, plus 7 byte overhead, plus 4 byte for the variable data type. So that means we will end up with 11 plus 1,000 bytes. So and now you can imagine the idea of having a row or page compression, especially a row compression, is that SQL Server now look for fixed data type, and the fixed data type always allocate the number of bytes the data type requires. That means an integer, for example, requires 4 bytes. A big int requires 8 bytes. A character, also not a varchar, a character of 8,000 bytes requires 8,000 bytes, even you insert a null. And that is where row and page compression comes into play. So SQL Server will automatically detect these kind of data type and will try to reduce the space. For varchar, you can imagine how it works when you have only 1,000 bytes in an 8,000 in a column, which can save 8,000 bytes. The row compression will automatically let's say, get rid of 7,000 bytes which are not used because you only insert 1,000 bytes, and therefore there's a possible space saving of 7,000 bytes for the record. So that means when you think about row and page compression, you have to understand your metadata. It doesn't make sense to create a table with a variable data type, and finally you apply at least row compression, because that doesn't make sense. Page compression can make sense. As already mentioned, page compression is something which will happen on top of the row compression. That means in our scenario, where we have a lot of variable length data type, row compression has no space savings, but the page compression will create a so-called dictionary in the header, which is part of the CD format. So the entire architecture of the page will change. And let's consider the following. You have a page where, what is a good example? Maybe you have a city, you have a customer with, and you save the city where the customer lives. So that means, I don't know, you have a lot of, I don't know, Texas, Texas or Houston or whatever, within your customer table. So that means the more often you have the same information in your page, the more likely it is that SQL Server will replace Houston by a dictionary lookup. That means it will create the, I would say, the Houston, the word Houston in the header, and now it will change the record, and whenever Houston is part of the record, it will not use Houston. Instead, it will use a pointer to the dictionary, which is definitely a space saving, because you can imagine the more often the record Houston or the word Houston is part of the page, the more possible space savings we will have. But you already understand that page compression have a complete different impact with regards to the compression feature. It requires much more CPU in order to compress and to decompress. Yeah, so that is the drawback of page compression. So let me scroll down. Again, I don't want to execute everything because this is I'm just proving what I already told you. So let me go down, and I hope this is, yes, partitioning. So again, this makes sense for me. I mean, everything else makes sense, but the scenario where you have, I don't know, a cluster table which doesn't have any kind of compression, and then you have a non-clustered index on top, which have, I don't know, page compression. For me, that doesn't make sense. For partitioning, it's a complete different story. So what we will do is, I think the partition function is already in place. No, it isn't. Okay, cool. So we create a partition function, which is a pre-requirement for creating a partition. And then we create a partition scheme based on the partition function. Okay, I'm not going into detail how to create a partition because this is definitely very well documented. And now we have a table which looks like this. So create table. And here we have with data compression row. And we say primary key clustered ID. So that means the table itself will become a cluster table. It can be either a heap or cluster table. So therefore, when we say primary key clustered, the partition which we align on the primary key, the class, which is by default clustered, will partition the entire table. That means we will end up with a balance tree based on the number of partitions. In our case, 5. Yeah, so there's always one remaining partition for all the values which are either less than 10 or more than 40, dependent on whether you change right or left as your partition function. So let me do this. Great. And now I can ask SQL Server about all the metadata about partitioning. And we can see, as mentioned, we have 5 partitions, and we can see all of them have a partition number, which is unique. It starts with 1, perfect. And here we can see the comparison. That means the very first partition is about greater than or equal to the minimum value and less than 10, which means everything which is less than 10 will go into this partition. So next one is this one. So equal to 10, less than 20. This is because we decided to go with the right partition function. And here in the end, we will have greater than or equal to 40 and less than the maximum value, which is in our case 40. Good. Let me now do the following. So I will change the compression type. So currently we don't have any compression type in place yet. Or do we have? Once again, just want to double check. And we have row compression. Sorry, we have row compression. And now the idea is we will apply a different partition algorithm. In this case, we don't want to compress the very first partition, but we want to compress partition number 3 with page and not row compression. So let me execute this one. When I now ask for the metadata, let me scroll down. We can see that we have Now, still 5 partitions, but 2 of them have different partition compression algorithm than the row compression, which we originally applied to the clustered index. So this makes sense for me because again, when you have very old data, you think about, I don't know, column store archive. When you have old data, maybe it's a column store. When you have, let's say, hot data, maybe this is no partition or maybe row compression. And something in between is maybe row or page. So it's up to you to decide. And later on, I will show you how you can determine the best algorithm. So for the compression, depending on the number of inserts and the number of updates, because you can imagine whenever I insert a record into a table which is compressed, it has its own CPU overhead. And for sure, the overhead is even more when you decide to go with a page compression. So therefore, as a general rule of thumb, when you have an OLTP system and you have a table which is not changing very often, that means you have just a few number of DML operations over the day, you can go with a page compression because then you definitely benefit from cost saving, not cost, space saving, on disk as well as with all the benefits we already discussed. And when you have a table like, I don't know, customer table where you insert a few records over the day, but it's still not some kind of a fact table, I would say. You can definitely consider row compression. When you have a fact table, like orders or whatever, I usually even set up a fact with row compression because the overhead for the row compression is in these days neglectable, and therefore a lot of space and for your fact table. I mean, you can imagine when you have a fact table which is increasing over time, so you get more and more records. So this is the best candidate for compression. When you just have a small table which is not changing over time, compression, but you don't benefit from the space savings. So therefore, it definitely makes sense to apply row compression for a fact table, even that there's some kind of a CPU overhead. So let me go down. Okay, there's more to cover here, but again, I don't have much time. Okay. Yes, okay, let's go with this example. This is important. So let me do the following. I will create a table another time. Maybe it's the same, I didn't remember anymore. So, and we can see it is a heap table. We don't have any clustered or primary key, which is per definition clustered, or we don't have any clustered index. It is a heap. So let me execute this one. I already did it. So now I can ask for the metadata. Page compression. At least the heap should be compressed with a page algorithm, page compression algorithm, which is not the case here, it's just metadata. Now we are inserting a few records. So this is the very first time that SQL Server asks several system pages, global location map page, PFS page, page free space page, in order to find a free page on disk, which is now going to the buffer. So because we always change and insert records in buffer, and finally the checkpoint will write the so-called dirty page to our MDF or NDF file to make sure that the recovery process is speed up. Otherwise, we don't even need any kind of MDF or NDF file. It's a log, which is important, by the way. So I inserted 3 records, perfect. And now I can ask for the metadata another time. And now something interesting happens. When we use this DMDB page allocations and not the metadata descriptions, which we use here. We just ask the metadata about the index, which tell us, okay, we have page compression, or at least we ask for page compression. So this view will tell us a complete different story. The page compression is not applied. We can see page compression is 0. That means even though we created a heap, it's a heap, yes, it's a heap, because we pass 0 instead of 1. In this case, the metadata is, I would say, lying, because this is what we ask for, but this is not what we get. We don't get page compression, right? So when we now dump a page, let's go with this one. This one is full. You can easily say or see that we don't have page compression in place, but this is equal. You can see it already. This is CD. This is a change descriptor format. So that means because we asked SQL Server for page compression and we inserted a few records into the table, the engine now automatically applies a row compression. So this is the CD array, the CD format, but there is no page compression in place. Why? It doesn't make sense. In this case, it doesn't make sense. So we will see it later on. So first of all, we have row compression, but we don't have page compression, even though you ask for page compression. So let me go down, and now we rebuild the heap. Alter table, table name, rebuild with data compression page. Just repeat what we want to have after inserting records into the table. And now we ask another time for the page allocation. And this time we can see, instead of having 2 pages, one which was full and another time, and another page which has 50% space available, SQL Server now use in complete different page. So I think I still have the other number available, which was 592. Now we will end up with 696. That means the other 2 pages are still there. They're still allocating page, but within the global allocation map page, the bit is flipped. That means now SQL Server can let's say, reuse the page for, I don't know, another index or another table, or even for the same table when we insert more and more records into the table and a new page is required. So that means SQL Server, you can see already the benefit. You remember before we had 2 pages, one which was full, another one which was half full. And now we will end up with 1 page only, and there's still a lot of space, not a lot of space, but 20% available. So we can see already, even though we are just inserting 3 records, we already have the cost saving or space saving. So let me insert a few more records after we compressed the heap by rebuilding the table. So let me do this. So we insert another 3 records. So finally, we should have 6 records, correct? And now when I go into the page allocation, we can see that the very first page, which was compressed after the very first rebuild of the index, is still page compressed, but the new records are not going to the page. Instead, SQL Server will repeat exactly what SQL Server did by inserting the very first 3 records. That means we now will end up with 3 pages. That means once we have page compression in place, you can see it here, no other record is going into the page anymore. And the new pages which are allocated by the storage engine, the pages are not compressed, at least not page compressed. Sure, they are row compressed. That is something which we already know. So I can rebuild the table another time. And I can ask SQL Server for the page compression, and Great. This time we can see that all the additional 3 records and the additional 2 pages, or the other way around, the 3 records will go to the page which is already compressed, and the other 2 pages are, I don't want to say gone, but the table does not know anymore that there are 2 additional, in this case even 4 additional pages which belongs to the table. So that means when I scan the table, the index allocation map will completely ignore the additional pages, because they don't belong to the table anymore, because otherwise we are reading the data twice. Okay. So now let's try to understand how a bulk insert works. And that is interesting. It is documented, but I mean, yeah, sometimes, at least when I read the documentation, yeah, I'm not recognizing these kind of details. So therefore, it is good to have examples to understand how it really works and how Microsoft is trying to explain what will happen. Sometimes that doesn't work for me, so I need an example. So what I did is, or what we are going to do is, we are creating a table with page compression. So I have a CSV file, which is a copy of the sales order detail table, which is nothing else than a copy and extract of the sales order detail table from AdventureWorks. And I have a format file here, which is an XML file in order to have the right schema. So that means I'm now reading the CSV file from disk, and this is the content. So now what I want to do is, I want to insert 120,000 rows into the empty table, which has page compression. So let's do it. So insert and select from CSV. Okay, cool. All records are inserted. And now I ask SQL Server for the page allocations. And what we see here is no page is compressed, at least not page compressed. Okay, so now I ask myself, I inserted 120,000 records. You can see we are allocating a lot of pages. Every single record is a page which has a size of 8 kilobytes. So I want to use page compression because maybe I have a big space saving here. So how can I do it? So the only way I can do it is, let's truncate the table. And this time, we ask SQL Server to insert the records with a tab lock. A tab lock means we have an exclusive lock on the table. That means no other concurrent thread can insert a record into the table because of the lock which is required, which is an exclusive lock. Inserting record means exclusive lock. And we will hold the exclusive lock on the table, not on the record. So therefore, any kind of or when another thread wants to read, insert, update, delete, or whatever records in the table, the entire table is locked until the insert is finished. So let me run this script. Because SQL Server can now rely on the case that no other thread can change records in between, insert, delete, update, or whatever. This is that SQL Server will now apply page compression. So we can see we have less number of pages available, therefore less space on disk as well as less space in memory, which is definitely what we want, right? But this is the only way to do it. Now you have a problem. When you know it, you can go one step further. Let me do this. Same table as before, page compression. We can, yes, this is just to make sure. Okay, there's already Ah, yeah, 1 second. 1 second. I'm a little bit lost. Here. Yes, usually I have separate index creation script. But this time we have a heap, same as before. But now the heap has a non-clustered index on column 4. It really doesn't matter. At least we have a B tree based on the heap. That means in our B tree, we have a so-called record identifier, which is nothing else than the page, the file ID, and the slot ID. Slot ID as well, I guess, to the heap. So that means we have two structures, a balance tree and the heap. So let's do it. We are now inserting 10,000 records again with tablog, because we already know that the only way to apply page compression is by using a tablog. Let's do it. This time I'm not reading from disk, just another scenario. I'm just using AdventureWorks 2022, but it's exactly the same. We are using tablog, and that is what really matters. So, okay, cool. 10,000 records are inserted. And now we ask SQL Server about page compression. Do we have page compression in place? No, we don't. So it means even though we have a tablog, an exclusive tablog on the table itself, right? No other process can change data in between. Any kind of DML operation is completely blocked. There's no page compression. The only way to get rid of it is, and that is something you have to consider, do you want to bulk insert a record into a table where you want to have page compression when you insert the records? Then you have to drop the index, the non-clustered index. You have to insert the record with tablog into the heap. And now you will rebuild the non-clustered index, which is in most cases even for sure the more, the better way to do it, because when we insert records into a heap with a non-clustered index, we don't have just one insert into the heap. No, we have another insert into the non-clustered, into the balance tree. That means we are inserting twice. So often it makes sense to drop the non-clustered index, insert into the heap. Now we have the benefit of the tablog. We can have a page compression. And afterwards, we will rebuild the non-clustered index because this is definitely, in most of the cases, much faster, and we don't need to rebuild the entire table to have page compression. That means we are able to save one DDL, so DDL operation, which is creating the index or altering the entire table to get page compression. So the index is gone. And now when I ask SQL Server, you can see that the new records, only the new records, which I'm inserting, or which has been inserted after I dropped the index, these pages are page compressed, not the other one. But you know already what we need to do in order to have page compression for the pages which doesn't have page compression. We have to alter the table and rebuild the table. Okay, cool. CD format is something which I cannot cover. Maybe have another 10 minutes, I don't know. But this is nothing I can do within 10. It's completely impossible. Let me go to, let me go to this example here. I think this is a good one. Yes. Okay, so that was interesting, at least for me. So let me do, I need to bring something, sorry. So I will create a table. And you can see column 1 is of small int. So that means a small int is a fixed data type. We know already, maybe we will benefit from row or page compression, because when we only save 1 byte into a small int, maybe it makes sense to have row compression in place. So let's do the following. We are inserting 1 million records into the table, which is fast. Should be fast. Yes, okay, that's fine. So it means I inserted 1 million records into the table, and there is no compression in place yet. So after inserting the records, yeah, for sure I can ask for the length, and for sure we can see we have some kind of distribution. We have a length of 1, total number of records 1000, and so forth. So that means this is not the length of the byte, there is the length, this is the length of the number, which means we have something between 0 and 9. So we have total records of 1000. Then we have everything from 10 up to 99, which is 9,000 times in the data in the table, and so forth. So that means there's a possible cost saving when we now apply compression. So let's do it. So first of all, we ask for the number of pages. I don't want to run it. You can see it here, almost 200 pages. 200,000 pages, each of 8 kilobyte. So we can, okay, I have to run it because I need one of the example page. So that means when I now open when I dump a page, we can see that the record length here, the record length is always the same because we have a fixed data type which have 7 bytes of overhead, 2 bytes for the small int. So that means every single record has 9 bytes. So that's it, very easy. So when we now scan the entire table, and hopefully we have statistics on, otherwise I will do it now. So we can easily see that we are scanning the entire or all the pages which belongs to the table. Yeah? So 1,359 pages. So wonderful. What I want to do, or what I need to do now is, later I figure out that I need more space. So a small int is not sufficient. If I remember before, I'm running the database in simple mode, will take ages. So please believe me, this is a fully locked operation, which is 356 megabytes big. Again, I don't want to scan it. You can see how to scan fndb log. And now we need to search for the transaction name, which we have here. Yeah? So believe me, almost a little bit more than 350 megabytes. So when I now ask for the page allocation, we have much more. Yes, we have much more pages in place. So that means when I dump the same page as before, no, let's go with another page. It really doesn't matter. Let's go with this one. Let me dump this one. We can see what happens. SQL Server have a so-called forwarding stop. This is a so-called forwarding record or forwarded record, dependent on your perspective. So why? Because we have a fixed data type and we are changing from 2 bytes to 4 bytes, and the page was full. We know it already because we have a lot of records. SQL Server now will forward the record to a complete new page and just leave a forward stub to the page where the record is moved. So when we now go to the other page, we will see the record and we will see a forwarding record, means it will point to this page. That means we have a very intensive I/O workload now, because we will end up with, so last time it was an 8, this time it is a 7, 5,117 pages, which is 4 times more than before. When I now scan the entire table, maybe I count the table, I will end up with, you can already guess, or maybe you cannot, because we will end up not with just 5,000 pages, we will end up with 1 million logical IOs. Why? Because for every single forwarded record, SQL Server have to go to the page where the record was moved. It will read the record, and it will go back to the original page, to the next record, and will find another forwarding record. That means we have a multiplication of the number of, or the number of forwarding records is the factor here. It means we will end up with a lot more logical IOs. And you can imagine what it means in terms of performance. This is bad. Okay, we can, I don't know how much time is left, but let me first of all, let me finish this example, and then we can discuss whether I should go ahead or not. So let me do the following. I will create exactly the same table another time, inserting 1 million records. It's exactly the same distribution. Yeah, same as before. And this time I rebuild the heap with a row compression. So row compression means we now know that the format changed from a fixed variable type to the CD format, which means for a number which is 1, we are not using pages, and we can see that it is compressed, right? So we can see CD array, and the record has a length of 9, which is okay for the moment. Now we will do the following. We ask for the number of pages. Yeah, okay, 59. So it's exactly the same number of pages as before. And now what we will do is the following. We run an alter table rebuild. So we are changing from small int 2 bytes to an integer with 4 bytes, as we did before, within an explicit transaction. This happens immediately. You remember it took, I don't know, roughly 20 seconds when we did the same operation, the same rebuild on the fixed variable format. In this case, because of the way the CD format is structured, SQL Server, even though we change from small int to integer from 2 bytes to 4 bytes, SQL Server internally already detect that 4 bytes is too much space to save a number like 1. So that means there is no change required to save or to enlarge the data type. Because even though we say we want to have a big int with 8 bytes, SQL Server will not change the structure because there is no reason. 1 still, as the number 1, still only allocates a few bits, right? So why should the idea of having a row compression is to find the right data type for the right value. So even though I enlarge or extend the size from small int to integer to big int or whatever, there is no reason for more space because we already have a compressed version of the record. So that is the reason why we can change immediately the size of the record or of the data type. So again, I don't want to run it. We only use 828 bytes, not 365 megabytes in our transaction log. It is still fully logged, but you can see because we are not changing anything, and it's just a reminder in the transaction logs that someone asked to change the column type, that's all. So when I now ask for the page allocation, we can see that the pages are not, we don't have any page compression because we didn't ask for, we just have row compression. but the pages are still the same. That means there was no change. The record is still 9 bytes long. So once again, let me dump one. This one. And what we can see here is interesting. Because there was no need to change anything, there is no need to have a forwarding record. There is no forwarded stuff available. That means when I now do a count, we still have 1,359. So no change. We don't need to worry about forwarding records when we have row compression in place, because there is no need to change the structure. We don't need to change the architecture, the structure of the page, which is completely different when we do it in a fixed variable format, because for fixed data type, SQL Server have to make sure that we now can save 4 bytes instead of 2 bytes. Therefore, we need space in the page, 2 bytes more per record, which will lead to forwarding record, which isn't the case for the CD format, because this is the reason why we have a row compression in place. We just want to we ask SQL Server just to allocate the space which is required, even though we ask SQL Server to enlarge the data type. This is the way of compression, right? This is one big benefit. So we will see other drawbacks for sure. We will see page splits. We will see row overflow pointer and everything like this. This is something which I cannot cover because we are running out of time. I think, Kevin, I'm done because you asked me to do it for an hour. So are there any kind of questions? I don't even know whether you have a chance to ask questions. I have no idea. So
Yes. Yes. So while we were going, there were a couple of questions in the chat, and the big one here is, let me scroll back up to it. Okay. How would compression work in character-based languages like, say, Japanese, Chinese, Korean, or even Cyrillic?
Yeah, correct. So that's a good question. So whenever we are talking about Unicode, right? So Unicode usually needs 2 bytes per character. So when you have row compression in place, and again, you need to understand that page compression requires a row compression. That means when you ask for page compression, you automatically have row compression in place. It means we only need to cover row compression. That means when you have a Unicode and you ask for, and SQL Server usually asks for 2 bytes per character, SQL Server, the engine now automatically detects whether it is possible to save the character in a 1 byte fashion, I would say. If not, we still see 2 bytes for the character, even because it isn't possible to have it in the ANSI range, let's say.
Okay, makes sense. And there was one other comment/question that was kind of comparing this to a notion in routing called data duplexing, where if you have multiple bytes that have the same sets of zeros and ones, then you could mark it as with a special bit, and that way the router would just say, "Hey, I've sent you this byte. Just repeat it this many times."
I think the question is not about row compression. The question is about page compression, if I understand correctly. Is this about the dictionary?
Uh,
Because what I understand, no or
it,
no?
not quite. But it was more of a tangent of, hey, this is somewhat related. It feels like it's kind of related to the dictionary compression process and page level compression, but that it was related to
Yeah,
how routers operated.
or maybe to be honest, I have no idea about the comparison here. So I don't want to say this is true, and I don't want to say this is not, this is right. I have no idea. So maybe this is a good let's say, picture some people have in mind to understand how it works. Yeah, the CD format really completely works differently. So I can open this. I don't want to go into detail because this will definitely cover a lot of time to understand how it works. So I will just open, 1 second, an example of a record, which is here. So yeah, again, I don't want to go into detail, but you can already, you see already how complicated it is. We are talking about a short data region, a long data region. We have clusters in place. So they call it a cluster. Yeah? So dependent on the length of the record or the number of the records, it's horrible complicated to understand how row compression works. I mean, the fixed variable format is pretty easy comparing to the CD format. It took me weeks to understand how to, yeah, let's say, translate the hexadecimal code, yeah, in the page which has a CD, also change descriptor format, back to, yeah, to something which is readable. Yeah. So again, I cannot answer the question because I don't know how the other algorithm works.
Yeah, no, fair enough. Fair enough. And it looks like that was all of the questions that we have in chat.
Mhm.
So
Okay, cool. There's no other question. Otherwise, feel free to send me an email. Once again, I just want to show my email address another time.
yeah, of course.
Can I see it? Where I should have it? Here we have it. Here. Yes. So this is my email address. Right. So feel free to drop me an email when you have questions with regard to performance tuning. I don't know, whatever you have in mind. Yeah. I cannot promise to answer. I will give my best. But yeah, let's give it a try.
Fair enough. All right. So as we wrap things up, thank you again, Torsten, for diving into compression tonight. That was a great presentation. Very nice.
Thank you.
Next week, everybody, we are going to be in person at Tech Systems. So you can see all the details there at meetup.com/tripass, TRIPASS. 2 weeks from now will be our business intelligence, data science, artificial intelligence, all of the hot buzzwords wrapped all together. That one's going to be online. So until we do see each other at a future TriPass meeting, everybody, take care.
Thank you. Bye.